From this lecture onwards,
we're going to start studying about
the different scheduling algorithms. So in this lecture,
we are going to discuss the first scheduling algorithm,
which is first come, first served scheduling. So we will see what is this first of scheduling. How does it work? And if this is a good scheduling algorithm. So this first come, first served scheduling algorithm is by far the simplest CPU scheduling algorithm. And from the name itself, it is easy to understand that first come, first served scheduling means the process that requests the CPU first is allocated the CPU first. That means whoever comes first will be given the CPU first. So the first process that requests the CPU will be given the CPU. And then the second process will be given the second chance. The third process that comes will be given the third chance, and so on. So it is fairly a very simple method that can be followed. And it is also a very simple method that can be implemented. And also it is a simple method to understand. So the implementation of the FCFS policy, or the first come, first of policy, is easily managed with the FIFO queue. So FIFO stands for first in, first out. So this is a normal method that we follow in a normal queue. So what we mean by first and first out is the element that comes in first will be the element to go out first. That means the element that comes in first will be the element to complete its work and go out first. So it is very similar to the normal queue that we have in our day-to-day life. So think of this simple example where you are standing in a queue in order to pay your bills or something like that in front of a counter. So what happens is the person who comes first will be the one who will be given the chance to perform the activity first. So let's say that suppose this queue is for paying some kind of bills. So the person who comes first will get the first chance to go into the counter and pay the bill. And the second person will be given the second chance, and so on. So whenever a new person comes, he has to stand at the end of the queue or at the tail of the queue. And then this pattern is continue. So if you are following a very fair kind of queue, then a person who comes at the end will never be given a chance to go in first, or will never be given a chance to come in between any of the other members. He has to stand at the end of the queue. And also, if you are following a really fair queue, then whoever is standing in queue has to follow that pattern. Nobody will be allowed to take the chance until his chance arrives. So let's say that there are some old people standing, or some children standing, and if you're having a fair queue, they will not be given a chance to go into the counter unless their chance arrives. You cannot break this queue. So I'm taking this example because in this first come, first served scheduling, this is what is going to be exactly follow. So keep this in mind. And as I told you, FEF's policy is easily managed by a V for Q. So this is an example of a V for Q where elements are queued up like this, and then the first element is known as the head of the queue, and the last element is known as the tail of the queue. So when the head of the queue, which is this element, completes its execution and goes out, then this element over here will become the head. And if some other elements come in, then they will be added to the tail of the queue. That means they will be kept over here, and that element will become the new tail. So that is how a FIFO queue is followed. And by making use of this FIFO queue, this FEF's policy can easily be implemented because it is going to follow a first come, first served basis. So what happens is, when a process enters already queue, its PCB is linked onto the tail of the queue. So we have studied about the different state that a process can be in, and we know that when a process is ready to be executed, it will be in the ready queue. And when it is in the ready queue, its PCB, there is a process control block, will be linked to the tail of the queue. If we are following our first of scheduling, and then when the CPU is free, it is allocated to at the head. That means here we have a queue where the processes are queued up like this, and then they are all waiting for the CPU. So when the CPU is free, the process, which is at the head of the queue, that means this process will be given the CPU for its execution. And then the running process is then removed from the queue. That means once this process gets to CPU, then this process will be removed from this cube because it has already got the CPU for its execution. So this process will be removed, and this second process over here will be the new head. And then if some other processes come in again, they will be added to the tail, and that will be the duty. So that is how first come, first serve scheduling works. Now let us see if this first come, first serve scheduling is an efficient scheduling or not. So here it says that the average waiting time under the FEF's policy, however, is often quite long. So if we are following a first come, first serve scheduling policy or scheduling algorithm, then the average waiting time for each process is quite long. So let us see why that is by taking an example. So here let's consider the following set of processes that arrive at time 0. So here we have 3 processes, P1, P2, and P3, that arrive at time 0 and wants to use a CPU for its execution. And then the boost time indicates the time that the process will take to complete its execution. That means the time it needs to hold the CPU for itself to complete its execution. So the process P1 has a burst time of 24 milliseconds, P2 has a burst time of 3 milliseconds, and P3 also has a burst time of 3 milliseconds. Now if the processes arrive in the order P1, P to P3 and are served in FEF's order, then we will get the results shown in the following Gantt chart. So here let's say that processes arrive in this order P1, P to P3. That means P1 is the first process to arrive, followed by P2, and then P3. So if they arrive in this order, and we are using the first come, first serve scheduling algorithm, then we will see the results shown in this Gantt chart, in which it shows the waiting time for each processes and the time each processes take for executing in the CPU. So if you see here, process P1 was the first one to arrive, so it did not have to wait any amount of time. So it is 0, and it took the control of the CPU. So P1 is executing in the CPU. And how long will P1 execute? It will execute for 24 milliseconds because that is the best time for process P1. So it will execute for 24 milliseconds. And during the execution of P1, P2 is already waiting in queue, because P2 was a second one to arrive, and P3 is also waiting behind P2. So how long did P2 have to wait? P2 had to wait 24 milliseconds because P1 took 24 milliseconds to complete its execution. And once P1 completed execution and frees the CPU, then P2 will get hold of the CPU. And how long will P2 execute? It will execute for 3 milliseconds. So P2 executes for 3 milliseconds. And meanwhile, P3 is waiting in the cube. So how long did P3 wait? P3 had to wait for 27 milliseconds. Why is that? Because P1 took 24 milliseconds. Then the next chance was given to P2, which took 3 milliseconds. So 24 plus 3 equal to 27 milliseconds. So P3 had to wait 27 milliseconds. And once P3 gets the CPU at the 27 millisecond, it does its execution in the CPU. And it spends 3 milliseconds in the CPU, thus showing this last time in the Gantt chart as 30 milliseconds. So this is what happens in a first come, first serve scheduling algorithm. If the processes arrive in the order P1 to P3, these are the birth times. So as I said, the waiting time for P1 was 0 milliseconds. For P2 it 24 milliseconds, and P3 was 27 milliseconds. So what is the average waiting time? It is 0 plus 24 plus 27, 3. Because 0 is the waiting time for P1, 24 is the waiting time for P to 27 is the waiting time for P3, and total direct 3 processes. So we are adding up these values and dividing it by 3, and hence we get 17 milliseconds. So the average waiting time for this particular scenario, when we followed first come, first serve scheduling algorithm, is 17 milliseconds. Alright, now let's take another example. Now let's say that the same processes with the same birth time arrive in a different order. So let's say if the processes arrive in the order P2, P3, P1, however, the result will be shown in the following Gantt chart. So here in this chart, we are having the time each processes takes and has to wait if they come in the order P to P3 and P1. So remember that the burst time is the same like the previous example. P1 has a burst time 24 milliseconds, and P2 and has P3 burst times of 3 milliseconds. So here what happens is, they arrive in this order, P to P3 and P1. So P2 is the first one to arrive, so it did not have to wait, and it takes control of the CPU and executes for 3 milliseconds because the burst time of P2 is 3 milliseconds. Then the next one that arrived was P3, which was waiting in queue. So how long did it have to wait? It had to wait for 3 milliseconds because P2 executing 3 milliseconds. So at 3 milliseconds, P3 gets hold of the CPU, and that P3 also executes for 3 milliseconds because the burst time of P3 is 3 milliseconds. And meanwhile, P1 is waiting in queue because P1 was the next one to arrive. After P3, how long did it have to wait? We see that P3 completed execution at the 6 millisecond because the execution time for P3 is 3 milliseconds. So total how much time did P1 have to wait? It had to wait 6 milliseconds because P2 took 3 milliseconds and P3 3 milliseconds. So total of a 6 millisecond P1 had to wait. And then at the 6th millisecond, P1 got hold of the CPU, and it thus is execution up to the 30th millisecond because the bus time of P1 24 milliseconds. So in this case, let us see what is the average waiting time. So in this case, as I said, the waiting time for P1 was 6 milliseconds as we see here, and the waiting time for P2 was 0 milliseconds because it was the first process to arrive, and the waiting time for P3 was 3 milliseconds because it was the second one to arrive, and P2 3 milliseconds. So here if we calculate the waiting time, it is 6 plus 0 plus 3, 3. So if we calculate here, it comes out to 3 milliseconds. So we see that in this case, the average waiting time for the processes has reduced substantially. In the previous example, we saw that it was 17 milliseconds for the same processes but in a different order. So we see that, depending upon the order in which they arrive, and depending upon their birth time, the average waiting time in case of a first-come, first-served scheduling algorithm varies greatly. So this reduction is substantial. Thus the average waiting time under an FEF's policy is generally not minimal and may vary substantially if the process's CPU burst time vary greatly. So this reduction that we saw in these two examples is a great reduction. That means there is a difference between the first and the second example. Average waiting times were really different. 17 and 3 has a great difference between them. So the average waiting time in this is not minimal generally, and it may vary substantially depending upon the both times of the processes and the order in which they arrive. And also the next thing that we have to remember is the FEF's scheduling algorithm is non-preemptive. So we have already discussed about preemptive and non-preemptive scheduling. So when a process is executing in the CPU, if that process can be stopped by some other process, and if some other process can get the CPU while the previous process was still executing, then that is called a preemptive technique. But when one process is in hold of the CPU and the CPU cannot be taken away from it until and unless that process completes execution or waits for an I/O, then that is known as a non-preemptive technique. So the first-come, first-served scheduling algorithm is non-preemptive. That means if a process gets to CPU, then all the other processes have to wait until and unless process that either completes their execution or waits for an I/O. So that is why I took example of that queue in our day-to-day life. So until an analyst, the person who is at the counter, finishes his work, no other person can come and interfere in between. So only when he finishes his work in the counter and goes out of the queue, the next person in queue will get the chance. So FEF's scheduling algorithm follows the same policy. So that is what is written here. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU either by terminating or by requesting I/O. So this is what I just explained. Now the problem with FEF's scheduling is that the FEF's algorithm does particularly troublesome for time-sharing systems, where it is important that each user gets a share of the CPU at regular intervals. So if you are having a time-sharing system where each processes needs to get the CPU at reverse of time. It is not going to be possible in this FEF's algorithm because only when one process completes execution completely or goes to her waiting for IA state, then the CPU can be given to some other process. So until that, no other process can take control of the CPU. So if a process is having a very big burst time and said there is a big process with a big burst time, that means it needs a huge amount of time to complete this execution. The CPU what will happen until an analyst that process completes its execution? All the other processes in the queue will be waiting and starving for the CPU. They will not get it until and unless that big process completes its execution. So it would be disastrous to allow one process to keep the CPU for extended period. So this will not be a very good technique because that said that have so many small processes which needs very less amount of time to complete. But at the head of the queue, there is a big process that needs a big amount of time to complete. Then unless that big process completes execution, all the other processes, though they may have a very less burst time, will have to wait. So that is the bottleneck here. So if you're having some big processes, that means processes needing more time, then they are going to delay the entire processes that are waiting in the queue. So this is a disadvantage of this FEF's scheduling algorithm. So FEF's scheduling algorithm is very easy to understand, easy to implement, but it is not an efficient algorithm. So this is the first CPU scheduling algorithm that we know about. And moving on, in the following lectures we will be seeing more CPU scheduling algorithms which may be better than this and which may be having more advantages as compared to this FEF's scheduling algorithm. So as a basic, this is the first algorithm that you need to know about. And I hope this was clear to you. Thank you for watching and see you in the next one.